algorithm, notation, analysis, running time calculation. Analysis of algorithms. First, what is meant by algorithm? Algorithm is a finite set of precise instructions for performing a computation or for solving a problem. Algorithm means it's a finite set of instructions or steps to solve a problem. The goal of analysis of algorithm is to reduce the space requirements and time requirements of the algorithm. Comparing algorithms using running time and memory space requirements. For this, how to analyze the algorithm. The best algorithm requires less memory space and less running time. Then running time analysis. Running time analysis is finding how the running time increases as the size of the problem increases. By increasing the size of the problem, how much running time is increases. Finding this is running time analysis. Next, input size. Input size means size of an array. If it is polynomial, considering the degree of the polynomial. Matrix, number of elements. Binary representation of input, considering number of bits. Then in graph, here inputting vertices and edges. Then types of analysis. There are three types of analysis: worst case, best case, average case. Worst case provides upper bound on running time. Means it guarantee the algorithm not run longer than this value, and no matter what the inputs are. Whatever may be the input we are giving, the maximum running time is the worst case running time. Best case running time, it's a lower bound. Input is the one which the algorithm runs fastest. Next, average case. It provides a prediction about the running time, assuming that the input is random. Best case analysis means it's a lower bound on running time. Worst case means upper bound on running time. Average case means prediction about the running time. Example, finding the total cost by finding total number of times the statement is executed. Here for the first type of algorithm, array of 0, we are assigning the array values as 0. For first assigning cost C1, second C2, C1, third statement C1, fourth statement C1 up to n minus 1 C1. So total is C1 plus C1 plus C1 up to n C1. So total C1 into n. But the same thing is implemented like this. For I equal to 0, I less than n, I plus plus, array of I equal to 0. The same thing is achieved here. For this for loop, C2 cost. For this assignment, cost C1. So, n plus 1 into C2 means this for statement is executed n plus 1 number of times. For index 0 to n minus 1, means I less than n. I less than means I equal to n minus 1. For this, n iterations are there. Next, in the n plus 1th iteration, it checks this condition and the condition is false. So, it exits from the for loop. So, this for loop executes n plus 1 number of times. So, n plus 1 into C2. But this array of I equal to 0, it executes n times. Because in the n plus 1th iteration, this for loop exited because of this condition false. So, array of I equal to 0 is not executed. So, this statement executes n time and this for loop executes n plus 1 time. The total cost C1 plus C2 into n plus C2. Another example, here sum equal to 0, for this cost C1, for I equal to 0, less than n plus plus, cost C2, for this for loop C2, this statement C3. So C1 plus, total cost C1 plus C2 into n plus 1. This for loop executes n plus 1 time. C2, for inner for loop, executed n into n plus 1 number of times. So C2 into n plus 1 time. This operation performed n into n times. So n square times. So the total cost is C1 plus n1 C1 plus n plus 1 C2 plus n into n plus 1 C2 plus n square C3. Next, asymptotic analysis. Using asymptotic analysis, we are comparing two algorithms. Let f of n and g of n be the running time of two algorithms. Asymptotic notations, three asymptotic notations. Big O notation, first one is big O, next big omega, next big theta. I call this as big O notation, big omega notation, big theta notation. Big omega notations means if f of n, g of n be the two functions, f of n equal to order of g of n implies f of n less than g of n, less than. Next, big omega notation, it is f of n equal to big omega of g of n implies f of n greater than g of n. Greater than g of n. Big theta notation, asymptotic equality. F of n equal to big theta of g of n implies f of n equality g of n, means there exist two constant, one is less than and the another. Big O notation. Let f of n equal to 30n plus 8. The order of n or order of n. F b of n equal to n square plus 1. So order of n square. Of n square. For big O notation, we have to choose the maximum one. Here order of n square is faster growing than order of n function. That is f of b is grow faster than f of a of n. Okay. This is f a of n 30n plus 8. So the second function is lesser than f a of n up to this point. Then it grow faster than this function. So from this position f b of n grow faster than f a of n. Some more examples are there. Back to our example. Here both algorithms, the maximum power n power is 1. So both algorithms provide same order, order of n or big O of n. This maximum power is n square. So order of n square. Notations. Big O notations. Let f of n, g of n be the two functions. F of n equal to order of g of n if there exists a positive constant c and a non-negative integer n0 such that 0 less than or equal to f of n less than or equal to c g of n for all n greater than or equal to n0. Here n0 is here. From this point, the f of n is lesser than c g of n. This is big O notation. Here g of n is upper bound for f of n. Then big omega notation. Here f of n and g of n be the two functions. If there exists a positive constant c and a non-negative integer n0 such that 0 less than or equal to cg of n less than or equal to f of n for all n greater than or equal to n0. From this n0, f of n is above cg of n. So, cg of n less than or equal to f of n. If so, we can denote this as omega of g of n equal to f of n. Example. Next, big theta. Let f of n and g of n be the two functions. Here there exists positive constant c1 and c2, two positive constant, and non-negative integer n0, n0 such that 0 less than or equal to c1 g of n less than or equal to f of n less than or equal to c2 g of n for all n greater than or equal to n0. Okay. From this point n0, c2 g of n is bounded above f of n and c1 g of n is bounded below f of n. So that we can write like this: 0 less than or equal to c1 g of n less than or equal to f of n. Example: worst case, average case, best case. Worst case running time of an algorithm is longest running time for any input size n. So upper bound guarantee the algorithm never take longer than this value. Best case running time. Example, the data is already in sorted order. Average case running time. Example, searching an element. So linear search. If the search element is present in the first position, then we can say this is the best case. The worst case, the search is present in the last position, or the element is not present in the array, then it's a worst case running time. Average case means present in the middle of the array. Here each record is associated with the key value. Using the key value, you are accessing the record. Serial search means sequential search. Searching record one at a time. So pseudocode for the search, linear search. From first to nth location, searching one by one, comparing the first element, second element up to last element. If the position found, then the position is returned. Otherwise, returns null. Analysis. A number of comparisons just depends on number of elements in the list. If there is n location, then the maximum comparison is n. The worst case, two cases are there. The search element is present in the last position, or the element is not present in the array. In this case, it provides maximum running time. So worst case. The average case, all the keys are equally likely in a search. Second is, we always search a key that is in the array. The search element is present in the array somewhere. For example, if 10 records are there, search element is the first position, second position to last position. The average search is first, second up to 10 divided by 10. Then our average case is 5.5. In generalize, 1 plus 2 plus up to n divided by n, so that n plus 1 by 2. Average case analysis.